for inviting us. It's a pleasure to have this opportunity to present our research. This is, as Dimitri mentioned, this is a joint presentation with Zissis Poulos. Just let me give you a bit of background about Zissis. Zissis has been a postdoc at Rotman, which is the business school at University of Toronto. He's been a postdoc for about 3 years now. He completed his PhD in the engineering faculty, and then he decided he wanted to apply his machine learning skills in finance. And so he moved over to Rotman as a postdoc. And I think he's sort of converted himself into a finance academic now. He's going on the finance job market this coming year. Okay, so let's so here's our working paper, Gamma and Vega hedging using deep distributional reinforcement learning. The first thing people tend to comment on as far as this paper is concerned is the number of co-authors. And I must admit, this is a record for me, 7 co-authors. I've never had that number before. But one thing I've noticed is that it's not that unusual in machine learning to have, lots of, much larger number of co-authors than we usually have in finance, which is 2 or 3. I mean, if you look at, for example, the publications coming out of JP Morgan, they've typically got 10 to 15 co-authors. We've got a fairly big research group in our research center, FinHub, at Rotman. And, nearly all the members of the research group contributed to this paper. So that's why we got so many co-authors. It's perhaps worth mentioning that of the people who are members of our research group, we have academics such as Zissis and myself, but we also have a number of what might be called academically inclined practitioners. These are people who have a full-time job, but really their heart is in academic work. So, people like Jackie Chen and Junyan are, have full-time jobs with financial institutions, but, nevertheless manage to work for maybe 10, 15 hours a week with us. And we find that quite rewarding. Okay, so let me start by giving a little bit of background about this paper. The most important Greek letter when you're hedging options is, of course, delta. And, in considering hedging strategies, it might seem natural to say, well, what's the optimal way of doing delta hedging? And in fact, we have a paper that does that, a paper that's been published that uses reinforcement learning to come up with optimal strategies for delta hedging. But actually, in a way, that's not that interesting from a practical point of view, because traders, as this first bullet point says, traders are usually required to make portfolios delta neutral, or pretty close to delta neutral every day. It's sort of part of their job, and they can get fired if they don't do that. And of course, delta hedging involves trades in the underlying asset where transaction costs are typically very small. So we're focusing on 2 other Greek letters, Gamma and Vega. I don't need to define these Greek letters for this group. I'm sure everybody knows what Gamma and Vega are. Key things about Gamma and Vega, of course, are that they require trades in options to manage them. Trading the underlying asset isn't going to have any effect on Gamma and Vega. But, you've got to sort of take a position in another derivative if you want to handle Gamma or Vega. And the transaction costs in derivatives are much higher, which makes the whole problem much more interesting. And I said here, it can be 0.5% of the option price. It could be 5% of the option price. So we use reinforcement learning. For those of you who are not familiar with reinforcement learning, it's a machine learning algorithm it's designed for sequential decision problems. You take a certain decision now, the world changes, you revise, you take another decision, maybe in 1 day's time, the world changes, you take another decision a day later, and so on. It's ideally, it's designed for that sort of decision problem. And of course, this is exactly the sort of problem that we have when we're hedging. We set up a hedge position, but it's not a hedge position we can forget about. The world changes, we've got to revise our hedge position or rebalance our hedge position, and so on and so on. So now, how does reinforcement learning work? This sort of big picture way of describing how reinforcement learning works is that it's kind of a trial and error strategy. You consider lots and lots of different ways in which the world can unfold. And, it does require, a lot of data like that. And if a strategy that you're trying seems to work well, that gets positive reinforcement. That's where the word reinforcement comes from. And if the strategy doesn't seem to be working well, it has negative reinforcement. In our work, we make a number of simplifying assumptions. You could say that our work is sort of a proof of concept of a particular approach to coming up with strategies for Gamma and Vega. So what we assume is that the rebalancing takes place every day, and that in order to manage Gamma or Vega, an at-the-money option is available. So there's a portfolio of derivatives that are dependent on a particular underlying asset, and you can take an at-the-money option that is dependent on that underlying asset to help hedge your portfolio. Okay, and why do we choose an at-the-money option? Well, because it's quite efficient in the sense that it's got a fairly high Gamma and Vega compared with out-of-the-money or in-the-money options. So you're looking at this portfolio of options that you have on any given day, and you're saying, well, we're going to hedge delta at the end of the day. So we won't think too much about delta, but it's got a certain Gamma and Vega. To what extent should we hedge Gamma and Vega given the transaction costs that will be incurred? And the trader has to make a decision. That's the action that's taken to hedge Gamma and Vega. And then once you've done that, you, as a matter of course, as I said earlier, you make the portfolio delta neutral by trading the underlying assets. Okay, now to sort of make things simple, we assume no transaction costs associated with trading the underlying asset. But of course, the analysis could be extended to relax that assumption. But as I said earlier, we're focusing on Gamma and Vega hedging. So we assume that, the trader just at no cost trades the underlying asset to make himself or herself delta neutral at the end of the day. Okay, so as I say, reinforcement learning is all about sequential decision-making. So here's a little chart that indicates how it works. You start with in a certain state. State can be defined by, the asset price, what the Gamma and Vega of your portfolio is right now, and that sort of thing. You take a certain action and the world changes. You find yourself in a new state. There's a certain reward you get as a result of the action you took. And then you take another action. World changes. You find yourself in a new state. That's S2, and you get another reward R2. So if you're not used to reinforcement learning, you have to get used to the words that are used in connection with it. So it's all about states, which we've denoted by S, actions, and rewards. And when when Zissis takes over and explains what we've done, you'll find he uses those words quite a lot. Okay, let me, as a little aside here, let me talk about how successful reinforcement learning has been in other situations. It's been really successful at playing two-person board games. For example, two quite difficult two-person board games are chess and Go, and it's now much better than any human being at playing either of those two games. When I was younger, I used to play a lot of chess, and I was always interested in how computers can be taught to play chess. And there's a long history to this. A long time ago, somebody claimed that they had a machine to play chess, and what it was a human being who's quite a good chess player inside a box. So you put a human being inside the box, and the human being would pretend that it was a machine that was making the moves. So as I say, there's a long history to trying to come up with machines to play chess. But a notable event was when IBM's program, which was called Deep Blue, beat Garry Kasparov. That was in 1987. And the way Deep Blue worked was it was trained to play chess well by chess grandmasters. Obviously it knew the rules of chess, but it also got a lot of intelligence, you could say, from really good chess players in terms of the sort of strategies it should follow and that sort of thing. But it was quite a narrow victory, but it beat the world champion Garry Kasparov in 1987. And this program Stockfish, which is around now, is based on the same sort of idea, that you give the computer program lots of good information about good strategies to follow.
John, can I ask a clarifying question?
Yeah, sure.
Hi. Yeah, I don't know much about this reinforced learning. I'm just trying to understand the setting. Are we trying to learn the optimization problem, like in a numerical way, like the Go? Or are we learning the expectations, say the mean variance, those kind of things from the data, right? Because in the data, we also, even if we can solve the optimization problem, we don't really know like the variance, covariance, whatever that structure, or even trading costs down the road, right? So will the optimization or both?
Well, I think it'll become apparent as we continue. I mean, there's an objective that you're trying to maximize, right? So you have an objective function which you're trying to maximize. And it can involve expectations, but it can involve more than expectations, as we'll see, because very often in finance, we're not only interested in the expected return, but we're also interested in risks. So we'll get onto that. Okay, but yeah, you've got to specify your objective, and then there's this kind of trial and error strategy for finding out how you optimize that objective. But I'd like to, before we leave this slide, I have to talk about AlphaZero, because, AlphaZero was developed by a subsidiary of Google, and all Google did was give AlphaZero the rules of chess. Nothing else. It didn't give it any information about strategies or, how really good grandmasters play chess and that sort of thing. And then what the program does is it just plays against itself millions of times and learns. But what I emphasize about AlphaZero and the equivalent game for playing Go is that all the program had was the rules, and say it learned by playing against itself, and it was basically using reinforcement learning. So if reinforcement learning can learn to play a really complicated game such as chess or Go, then hopefully it can help us with some of our finance problems. Okay, so maybe this is coming back to your question, we are interested in taking sensible hedging decisions for a portfolio of derivatives that are dependent on a single underlying asset. Okay, so we'll say more about this portfolio of derivatives a little bit later, but it basically, at any given time, you've got a portfolio of derivatives that's dependent on one underlying asset. And what's your objective function? Well, we consider these three objective functions that are listed here. You can maximize the mean gain as a result of all your hedging decisions, minus 1.65 times the standard deviation of the gain. So, you know, if the distribution is normal, then of course that's the 5th percentile point of the distribution. We could minimize value at risk with 95% confidence, which, you know, is similar to the first one, except the distribution might not be normal. And then the conditional value at risk, which is the expected loss, you know, conditional on being worse than the value at risk. So those are the three objective functions that so what we're basically assuming is that the main objective of the trader is to, you know, avoid extreme losses, because each of these three objective functions sort of focuses on, you know, fairly extreme losses. We've talked about other objective functions. I mean, you know, one objective function that we might consider would be this one at the bottom here. K1 times the maximum of the gain 0 to the power alpha minus K2 times the maximum of minus gain L. So basically there we're looking at gains as well as losses. And maybe, you know, what we might do is put K1, I'll just give you an example. I mean, if we put K1 equal to 1 and K2 equals to 2, we're putting more weight on losses than we are on gains. And, you know, we might say alpha was 2 or something like that. So, you know, that's an objective function that we've talked about that, you know, might be more appropriate for some traders in that it's sort of weighting gains as well as losses. And you can obviously extend, you know, that equation as you want to. Now, as soon as we start talking about this sort of thing, the whole issue of time consistency comes up. And it's an important theoretical concept in sequential decision problems such as this. Basically, a strategy is time consistent, or maybe I should say the objective function is time consistent if the optimal strategy for that objective function for a given set of state variables is the same at all times. In other words, you know, if you have a certain set of state variables at time 0, and you take a certain decision, and then you have the same set of state variables at some future time, you will take the same decision. Now, maybe I'll go back a slide. These three objective functions are not time consistent, as is well known. The one at the bottom there, I think the one at the bottom is time consistent because it's a function only of the gain. Doesn't involve the, you know, the whole distribution of the gain. So there are, you know, there's been a lot written about how you can handle inconsistent objective functions. What we decided to do was to use reinforcement learning to try and optimize the objective functions subject to some constraints. So basically, rather than have an unconstrained optimization, we decided to deal with a constrained optimization problem. The two constraints are that the traders take a position in the hedging option at each time that's the same function of the state variables. which you could say is analogous to the time consistency condition. So even though the optimal strategy isn't time consistent, we insist that our strategy has this time consistent property, and that the position does not depend on the gains and losses so far. So you could say this is kind of like, a sunk, saying, well, we don't want to consider sunk costs. It's kind of analogous to that when, really whether the trader has made a huge gain or a huge loss, in the last month shouldn't affect how the trader behaves in the following month. So, we chose this constrained optimization problem because it seemed to make sense to us in terms of what the financial, how the financial institution might want the traders to behave. Okay, but I'm sure some of you may have thoughts on that. Okay, as I say, we regard what we've done as a sort of proof of concept because there's just so many different assumptions that could be made. We actually assumed values of 0 for the risk-free rate, the dividend yield, and the expected return on the asset. And we presented this paper at the CDI conference, and we were criticized for that. And maybe it's a valid criticism. So we've actually now been producing results that relax those assumptions. So we have reasonable non-zero values for the risk-free rate, dividend yield, and expected return. I'm pleased to say that our new set of results don't seem to alter the nature of the results that we will be presenting today. In other words, the general nature of the the results that we're going to present are for the non-zero values for these parameters are much the same as the values for zero, have the same general form and sort of same general improvements over other strategies that we get for the zero values. Okay, so let me say a little bit more about the setup that we have. We assume that the options entered into with clients arrive stochastically. If you look at most of the literature on hedging, talks about, well, let's suppose we have a position in this one option. How do we hedge it? One of the nice things about this reinforcement learning setup is that we can be a little bit more realistic, and we can say what the trader has to worry about is options that arrive stochastically. So we can assume a stochastic process for the arrival of the options, and at any given time, the trader has a portfolio of options that have to be hedged. So what we assumed was a Poisson process for the arrival of client options. So these are options which you entered into with your client that you have to hedge. We assumed a very simple intensity for the Poisson process of 1. The options are at the money and have a 60-day maturity and are equally likely to be long or short. That's obviously, again, a very simplifying assumption. But in a practical application of our approach, what the trader has to do is to sort of make an estimate of the stochastic process that's leading to the arrival of options from clients. As I say, we regard what we've done as a proof of concept. So at any given time, the trader has to manage a portfolio of options. Some of the options are these client options that we've been talking about that arrive stochastically, but also the trader every day is potentially entering into options for hedging. And so you've got two categories of options, if you like, in the portfolio: the client options that have to be hedged and the options that you're using for hedging. And that's I mean, you don't actually really need to distinguish between those two because, you know, the gammas and vegas of the options that you've entered into for hedging are just as important as the gammas and vegas of the client options. You have to have a time horizon in reinforcement learning. In the results that we'll be presenting, we used a time horizon of 30 days. This is somewhat arbitrary, and we are looking at different time horizons. Our sort of preliminary results suggest that actually the strategy doesn't depend on the time horizon to any great extent. Okay, so in finance research, I guess we're always looking for, economic sort of insights, if you like, or economic results. One thing that I think our research can do is reach conclusions about the economics of offering options to clients and the economics of trading. I mean, what we can do, and we do this a little bit in the paper, is we can assume that the spreads that the financial institution earns on the client options are the same as the spreads that the financial institution has to pay on the options that are used for hedging. I mean, you don't have to make that assumption, of course, but that's the simplest assumption to make, that there's a certain spread in the market and it's the same for client options as it is on the options for hedging. And then you can ask, well, how profitable is it to actually trade these options? And, the interesting question is, I mean, obviously, if you've got, a really active market, lots and lots of client trades coming in every day, then it's going to be fairly profitable because, a trade in one option could, hedge 20 different client options that you've happened to have entered into that particular day. But if, it's relatively rare for the client to come up, for clients to trade a particular option, then it's nothing like as profitable. And that can be quantified with this sort of approach. Okay, so this is my last slide before I hand over to Zissis, and I'm sort of, in a way, introducing his first slide because the standard reinforcement learning formulation that's in all the textbooks maximizes expected return. I mean, that's, expected return is a very well-behaved variable, and, maybe that ties in with the question I had earlier. In many finance applications, including this one, we're interested in optimizing an objective function that reflects risk as well as return. So we have to think how we're going to modify the standard reinforcement learning formulation to build, risk as well as return into it. And this is referred to as risk-aware reinforcement learning.
John, I wonder why you title it as hedging. Is it like a more general objective as what you're doing as a vega and gamma investment? I mean, you're doing mean variance investment in a sense, right?
Sorry, we're doing mean variance.
Yeah, essentially you're investing in the vega and gamma direction, your data hedge, instead of hedging it. I mean, yes, you're controlling risk in the maximum direction. It's a more general objective in a sense, no?
No. And that's a good point.
Because when you're mentioning,
we don't have to have this in a hedging framework. It could be in a more general portfolio management framework. Yeah.
Yeah. When I was reading about the hedging, I said, okay, what's wrong with the traditional hedging calculation? So it has nothing wrong with the traditional hedging calculation because here is more of an investment decision, but empirically done to identify which path of investment give you the high return of risk in a sense, based on your criteria.
Yeah, that's right. Okay. Maybe if there are more questions, we'd be happy to take them now. I guess I want to get out of your screen sharing. Stop share. Okay, I'll stop share. Let Zissis in to share his screen now.
So the question is, I'm curious, what benchmark do you use to compare your hedging approach against? Hedging using the Black-Scholes Greeks? That was one question, right? So is there so you're having proof of concept, but anyway, I'll paraphrase Dimitri's question. So you're having proof of concept, but do you have any evidence that this approach works better than other approaches?
Well, the results that Zissis will present do compare what we're doing with other approaches. So, okay, you could decide, well, I'll totally hedge gamma and that'll do some good as far as Vega is concerned, or I'll totally hedge Vega and that'll do some good as far as gamma is concerned. So we do compare with those approaches. There may be other comparisons that you would suggest we should consider, but as you'll see from the results we present, it's sort of the simplest thing to compare is, are we doing better than just taking the position in this option to totally hedge out gamma or totally hedge out Vega?
And then there's a second question that I'm highly confident you haven't answered, but it might be worth thinking about for the future. So you have a particular stochastic process for how client orders arrive, and even for volatility and whatever any other parameters, right? Mm-hmm. And let's suppose the underlying stochastic process changes. Does your reinforcement learning, how quickly can it learn the new process?
Well, yeah,
I'm sure you don't have the answer.
I should hand over to Zissis now, but I mean, we will be presenting some results on that, because we'll be saying, well, let's suppose you estimated this particular stochastic process, and actually, well, actually, this is the process for the underlying asset, but if, you can obviously carry out some sensitivity to sort of how well does it work if we are wrong in terms of the process that we've estimated. So that's the sort of, that's the sort of test that you can do. And Zissis has got a couple of slides to illustrate that.
Anyway, I think we should let Zissis carry on, given the time constraints.
Yeah. Hi, everyone. Thank you. It's a pleasure to be here. As John said, it's exciting for us to be able to present our most recent work in that space. So again, as John said, if you have a risk measure in your optimization, right, it's unlikely that the standard reinforcement learning framework will work as is, because it's explicitly trying to minimize or maximize an expected value. Now, there's exceptions. If for example, you can rewrite or express your risk measure as an expectation of a nonlinear function, let's say, you could do with standard reinforcement learning frameworks, you could do that. But if you care about more general cases, then you have to move towards this risk-aware algorithms, right, that are gaining a lot of popularity more recently. And a lot of the research there has actually been motivated. The research that tries to close that gap has been motivated by tasks in finance, such as hedging and portfolio optimization, as someone else mentioned before. If you go back to 2016, Tamar and his team shows us how we can use a reinforcement learning optimization, where during training, where when I say training, I mean learning a policy that optimizes something, optimizes an objective. During that phase, you can at the same time estimate not only the mean of your terminal gain distribution or terminal loss distribution, but also the variance and possibly other higher moments of the distribution, right? And if it happens that your objective function is a function of these moments and the mean, then you can optimize, right? Now, it's, in fact, we used that method for the delta hedging paper. I think it was published 1.5 years ago. There are some shortcomings here. This formulation can't accommodate or can't support any arbitrary objective function that includes a risk measure, and it's also very computationally intensive because you're trying to estimate in parallel different moments of the return distribution. In fact, if I remember correct, we had to use 8 different deep neural networks trying to coordinate in order to estimate different moments and then estimate losses and inform how the policy should change. So it gets really messy really quickly. A more natural way to work with risk-aware reinforcement learning is with distributional reinforcement learning, which was introduced a little bit later. If you fast forward to 2018, we have a thread of research that is proposing that while you're learning a policy, you model, you estimate or approximate, if you want, the entire distribution of the terminal return, right? The entire distribution of the total accumulated gain, let's say, at the end of your horizon. Some of the early works were doing this as follows, right? They would say, well, I'll have a predetermined fixed set of points on my horizontal axis, and that's basically the terminal return values, right? And then what I'm going to be learning during my training phases, I'm going to be learning the probabilities of these values, right? And one of these algorithms is called C51, just because they're using 51 fixed points. Why 51? Well, it seems to be a good trade-off empirically between complexity, computational efficiency, and approximation or representation capacity, if you want, the ability to represent this distribution as well. Now, if you can do that, right, if you can estimate the distribution, then you can measure any attribute of that distribution, including expected shortfall, focus on specific quantile and measure your value at risk, or even mean standard deviation, right? And then if you can measure these values, then you can tell how well your policy is doing, and if your policy is improving, right? So that's the whole point in reinforcement learning. You learn something, it's not good, you have to improve it. So you have to have a measure of how well that policy is doing, right? So by estimating the distribution and measuring this, measuring risk on the terminal distribution, you can learn whether you're improving or not. If you work with value at risk and expected shortfall, there's another algorithm that feels more natural. It's the work by Dabney in 2018, distributional reinforcement learning with quantile regression. Now, instead of having a fixed set of points, what you have is a predetermined set of quantiles where its quantile has the same probability, so 1 over the number of quantiles. And what you're learning during training is how to adjust the position of these quantiles so that what you're estimating matches your empirical distribution, right? It's the one that you get by sampling over episodes, over sequences of hedging periods. And that's exactly the one we're going to be using in that work. I'm going to explain a few more things about it once we will look under the hood in a bit. But before I do that, let me just, yeah, is that the right one? Yes. Okay. So how does, just a high level idea of how distributional reinforcement learning works, right? You remember that chart that John was showing before? You had this sequence where you start at an initial state, you take an action, the stochastic dynamics in the environment move you to a next state, and so on, right? And you have to make decisions along the way that maximize or optimize an objective, right? Say you're in distributional reinforcement learning, say you're at time I-1, you did something, you took an action, right, based on your current policy that you're trying to improve, possibly, and you landed in state Si. You received some reward from your system, from your environment, call it Ri, and now you're in time I, right? Just imagine now that, you you only have 2 possible actions to take. That's not realistic. In reality, the action space is continuous, right? So things are more complex, but for the sake of simplicity, you have this dilemma, right? Do I take AI action, or do I take action AI prime? Now, suppose that your framework, your algorithm maintains an estimate that says, well, if you're in state SI and you take action AI, this is how I think your terminal distribution is going to look like. Whereas if you know, the blue one, if you are in the same state but take the other action, this is what I believe your terminal distribution will look like, and that's the red distribution. So you have a way to discriminate between actions, right? How? By just measuring the properties the attributes that you're trying to maximize for in your terminal distribution at its time in your period, right? So if you want something that has thinner tails, you'll choose the action that produces that distribution in the end, right? And then now, how do we estimate those things? I mean, in reality, what happens is the actions themselves are modeled as neural networks, right? Neural networks are function approximators. So actions are functions of states. What do I do, right? When I'm in state SI. And the distributions themselves are also modeled using neural networks as well, right? If you wait for 2 minutes, you'll see exactly how the architecture looks like. But before I do that, I'd like to make the discussion about states, actions, and rewards a little bit more concrete, because we've been talking about them. Now, when you design your optimization framework in reinforcement learning, the states are everything that you want your trader, in our case, to know about the environment. A good rule of thumb is to include the minimum number of states that are informative for the problem at hand. You can add more states, but then what happens is you have to take into account, well, is this a realistic assumption? Is it going to, if it is, then maybe I should include the states. But also, if I include the states, I increase the complexity of the search space, because I have to take into account many more different possibilities. So there's a trade-off between complexity and being practical and pragmatic about your design. In our case, the states are, of course, the price of the underlying asset, the total gamma and vega of the portfolio, and those are practitioner gammas and vegas, and the gamma of the at the money and the vega of the at the money option that's used for hedging in order to manage your portfolio gamma and vega. The action that you take at its time is the positions you take in the hedging at the money hedging option, right? And the reward is that you receive from the environment each time you take a step is the profits, the P&L of the portfolio minus explicit transaction costs associated with, you know, the premium you pay for, associated with the transaction cost induced when you take a hedging position in the at the money option. I think it's something like the P&L, the accounting P&L formulation, or if you want the clean P&L minus explicit transaction costs formulation. Okay, now knowing this, let's take a look at the architecture. It's not as scary as it looks. It's not. So, I mean, it scares me right now, but okay. Anyway, so let's start simple, right? So basically, if you look at the bottom box, that we say, you know, we say that's where the environment lives. Basically, the environment covers everything, right? What is the environment? It's the trading environment. What does the environment do, right? It stepwise simulates the episode, right? For multiple episodes, right? What it will do is will simulate asset price movements. It will compute practitioner gammas and vegas after you take an action. It will figure out whether there is an incoming client option, if it's a long or short, and so on. So it will just gather all the data and compose all the data necessary so that it can move you from one state to the next, all right? Conditioned on what action you took in the current time step. And it will also compute what your reward is, which is the formulation we talked about in the previous slide, all right? So the environment dictates what your state is and computes your reward. Now, the state is fed into a neural network, that one on the left. That neural network is your policy network, or if you want, a neural network representing your hedging strategy. It takes as input state, and it tells us what should we do, right? So that's why it's the policy. What should my actions be given that I'm in that state? Now, the actions that we have is actually a percentage of the maximum hedge that we permit. I can talk about it a little bit. What we're doing is we're deciding what's the maximum hedging position that you should take, so that at least one of those two criteria is true, that your gamma hedge ratio is your gamma after versus your gamma before is between 0 and 1, and your vega after hedging versus before hedging is also between 0 and 1. You might not be able to satisfy both conditions at the same time, but we need at least one of them to be true. Why? Because if we do that, if we constrain the action space, we don't evaluate actions that are known to be suboptimal, right? So then we have fewer wasteful simulations, we convert faster. So there's a little bit of domain subject level expertise in here, just telling the algorithm that, okay, you shouldn't go there. Regardless, the actions are decided by this neural network, along with the states that were input to the neural network. They're fed into that other neural network on the right. That's what we call the critic network. What is the critic doing? It's very simple. It takes as input the state and the action that the policy took, and estimates what would the terminal return would looks like if I take this if I take this action in that state. Now, you have an estimation of the quantiles, right? Then how do you improve your estimation? Because probably it's going to be pretty bad in the beginning. You don't know much. You haven't sampled enough episodes, so you don't know how the empirical distributions look like, right? So that's where we use quantile regression. The neural network is estimating something. It's probably wrong. The empirical distribution looks like this. You compute the Huber loss actually between the two. That's differentiable. What does this mean? You can apply gradient descent on this critic network to improve its ability to estimate distributions of future returns. At the same time, since you have the quantiles of the distribution, the estimated one, you can measure the objective function. And since this is a minimization problem, you also get gradients that will minimize that objective function. And those gradients are passed back to the policy network, the neural network on the left, so that you change its parameters towards the direction that minimizes the objective function. So that next time that this network sees the same state, it will take an action that is better than the one it took before with respect to the objective function. In the beginning, as you can imagine, there's always an interplay between the two. In the beginning, you can imagine the distribution network, the one that estimates the distribution, is not doing a good job. So the actions are not well informed. So there's a lot of exploration taking place. You learn policies that look random, but then as you're improving your critic network and you get better estimations of the terminal distribution, you end up improving your actions as well, to a point where you converge to some local optimum, right? I hope that gave a little high level, the architecture of what's going on. I'll just, move to results. Suppose we have these assumptions and this architecture, what do we get, right? In our first test, as John mentioned, we have a simple scenario where asset dynamics are governed by geometric Brownian motions, right? We set the initial volatility fixed to 30%, initial asset price to 10, and we have the 0 values for expected asset return, dividend yield, and risk-free rate, as John said, this being a proof of concept. And we use a lot of paths, a lot of episodes to simulate and train and learn policies, and we test these policies on 5,000 different test scenarios over the 30-day period, where we value the portfolio at the mid-market on that 30-day mark. Let's see how the results look like. Now, in this table, all right, we have different objective functions on the left. The table is divided into 3. You have 50 basis points for cost, 100 and 200 basis points as well. The transaction costs are for hedging and for taking position in the hedging option. they don't affect delta. As we said, we assume it's costless. So when you look at the objective function values, the second, third, and fourth column, you see delta is unaffected by that. It has specific values for that objective function. That's okay. Then you have delta gamma. In this result, by the way, I forgot to mention, we don't care about vega. There's no volatility of volatility. So we remove the states that have to do with vega, right? So we're only focusing on gamma. So the delta gamma policy gives you clearly an improvement over a delta neutral policy, but you can see that the reinforcement learning agent does even better than the delta gamma neutral strategy.
Let me interrupt and give you the 8-minute warning.
Sorry?
8-minute warning.
Oh, okay. I'll speed up. Okay, so thank you for that, Anil. So we see an improvement with respect to the objective functions. Another interesting observation is that the agent understands how to adjust its gamma hedging with respect to transaction cost, right? So if the transaction cost increases, the agent learns to reduce the amount of gamma hedged. You can see this with the gamma hedge ratio. Just for the sake of simplicity, just imagine that the bigger the ratio is, the more gamma you're hedging. So you see as you're moving to higher transaction costs, the ratios drop. As you increase your transaction costs, the expected loss from trading increases. That's expected. But fortunately, when the transaction cost doubles, the expected loss does increase, but it's not double, right? Then here there's a chart that shows the distribution of gains for a VAR 95 reinforcement learning agent, and we compare against the delta gamma neutral and delta neutral strategies. So blue is delta neutral, orange is delta gamma, green is reinforcement learning. If you zoom into the tails, you can see that our probability of experiencing very large losses, it's much lower compared to the other strategies. And you will also see that the mean loss, if you want, of the reinforcement learning agent policy is shifted to the right? So that's also desirable. Now in the second test, which is more, where volatility is uncertain, right? We're employing a special case of the Sabre model developed by Hagen in 2002. The nice property here is that you can have a good analytical approximation of European options implied volatility, which we can use to value the portfolio. The parameters are there in the bottom. Volatility 0.3, initial volatility 30%, like in the geometric Brownian motion test, and correlation at -0.7. The table now looks like this. It just includes the delta vega strategy as well and the vega hedge ratio. The idea is similar as before. We have a twist here. We have 30 days and 90 days at the money options used for hedging. 30 days options are more relevant for managing gamma, longer maturity at the money options more useful for managing vega. And in those two different scenarios, we have money options or only 90-day options as the hedging instrument. We'll see if the agent can tell the difference between the two. Now, if you take a look, you'll see that we have similar conclusions. Objective functions improve when we use reinforcement learning compared to the simpler strategies. Similar conclusions in terms of hedging less aggressively as the transaction costs increase. Similar conclusions about expected loss, but also more importantly, or equally importantly, you can see that when we use 30-day at the money options, the performance of the reinforcement learning agent, but also the gamma hedge ratio indicates that you're closer to delta gamma neutral, right? You just lean towards that kind of strategy. Whereas if you use the scenario when we're using 90-day at the money options, the behavior of the reinforcement learning leans towards delta vega neutral. You can see that the vega hedge ratios are larger compared to the gamma hedge ratios for these scenarios, right? And it's the other way around for the 30-day case. We also have a frontier here where we took different percentiles for the value at risk. We trained different reinforcement learning agents. I believe this is the 100 basis points transaction cost case. And we built this frontier we also map into the same plot, which is a mean versus variance plot trade-off. We mapped the delta neutral strategy, the delta gamma neutral, and the delta vega neutral strategy. And you can see that the properties of the agents are attractive in all cases compared to these other simpler strategies. Now that relates to a question that we had before. We also try to see what happens if you have model misspecifications, right? To some extent. So for example, what happens if you overestimate or underestimate your initial volatility or your volatility of volatility, and when you test those values, the realized values are different, right? We found that generally the framework is robust. There is degradation, right? There will be degradation, that's expected. But interestingly, we found that when you overestimate the parameters, when you trade, let's say, with higher volatility, and your realized volatility is smaller, then you're more robust than the other way around, where you underestimate the realized values. I have just 3-4 minutes, so maybe I'll just cover 1 or 2 of the tables. This is the first robustness test where the volatility that you estimate during training is different than the one that's actually realized. All right, let's assume that the realized volatility in the Sabre model is 0.3, and in the left column, those are the ones you guessed. Well, in the in the row where you have v equals to 0.3, your guess was correct. So that's the ideal scenario where you got it right. As you deviate from that, you see that you have degradation in performance. But your degradation, you're much worse if you underestimated the parameter. So if you train with no volatility, BSM essentially, or volatility 0.15, you see that the values of the objective functions are worsening. Whereas if you overestimate with volatility 0.45, they are relatively close still, and similar conclusions for the other metrics. And the same, similar observations here as well, where you train with different initial volatilities, and your realized initial volatility is different. And both in this case, we assume that your volatility, you guessed it right. So you have the correct estimation there. Similar conclusion, right? If you remember, the realized one is 30%. So that row with 30% is when you had the correct guess. Again, you have degradation as you move away from that, but the degradation is smaller when you're overestimating the parameter, when you train with 40% or 50%. I think John talked about the economics of trading derivatives already, so I'll just skip that. Again, as John said, this is a proof of concept. There's several possible extensions here that have to do with theoretical support for this work, but also for practical extensions. We want to figure out how, as Neil said, how do we behave when we incorporate different types of stochastic processes in the test environment? For example, when we have jump models and so on. How does this work for exotic options? Because there could be some interesting behavior as you're approaching the barrier. You have discontinuities also in your Greeks, right? How does this work if you have a choice between multiple hedging instruments in its period? How does the trading desk still make money? How does it depend on the average number of client order per day? And another thing we could extend towards is the use of convex transaction costs or fixed transaction costs plus some proportional model, which would disincentivize very small trades, let's say. I don't have anything else to say, so I think we're just open to questions. And thank you for this opportunity again. Big pleasure to be here.
All right, thanks very much. I'd like now to invite anyone who has a question to feel free to unmute yourself and ask the question using the microphone. I see there are a couple of questions in the chat. I don't know whether they're new or whether I overlooked them before. Anyway, from Philip Rosenthal, slide 27. Could you explain again why delta vega hedging is worse than pure delta hedging for a 30-day period and sometimes even for 90 days time frame?
Let me read the question too.
Well, I mean, I mean, a 30-day option is going to be better for gamma because the shorter the maturity of the option, the more gamma it's capable, the more gamma it's capable of hedging, right? Whereas the longer the maturity of the option, you know, it's got less gamma but more vega. And that's really what we were trying to illustrate there, I think. You know, you said that for sometimes, I think delta vega always looks better than delta gamma for the 90-day option, and it's the other way around for the 30-day option.